Now this is all about section 5.2. And so these are examples related to the properties of the integral. Now let's start off with a problem that uses the splitting up by limits property. So suppose that for a certain f chosen, we have that the integral from 1 to 2 is 1, and the integral from 2 to 3 of that same function is 5. We want to find the integral from 1 to 3 of that function. Well, when we take that integral, one of our properties is that we can always split up an integral with respect to its limits of integration. So we take our lower limit and we go up to some intermediate value that's in between our lower and upper limits of integration. And for the integral which is attached to our original lower limit, this intermediate value is going to be the new upper limit for that integral. For the integral which takes on the old upper value, that intermediate value is now the new lower value for this integral. But now at this point, we actually know these integral values. And so it's just simple algebra. Here's the property that I use here. If a is less than b, which is less than c, and I take the integral of a continuous function, or at least, some integrable function, then this is the same thing as the integral of f from b to c plus the integral of f from a to b. That's the property I use there. What I specifically gave were these two integral values. But we could have just as easily given, say, this integral on the left value and the right integral to find the middle. Or maybe the middle and the left to find the right. A lot of different ways you could ask this problem that involves splitting up due to the limits of integration. Going on to the next slide here. Let's graphically argue why this property holds. Well, suppose we have some Riemann integrable function from a to c. So what we can have is that, of course, it's a continuous function. Or we can have that it's discontinuous, but for only finitely many jumps. And in this instance, I just gave it, one jump. Now what we're going to do is we're going to take some point B in between A and C. And remember what the integral means. if I call the area of this region between a and b underneath the function f, a1, and I call the area underneath f between b and c as a2, then the integral of this function f is the same thing as a1 plus a2. But what is a1? Well, that's just the integral from a to b of our function. And what's a2? Well, just by definition of the integral, that's the integral from b to c of f. And likewise over here, I drop down here, make my little vertical lines, and now I have some a1, a2. Basically, you'll get the same thing, even if it's a function with a jump discontinuity rather than a continuous function. So the important thing here is just to maintain integrability of f, and then you have this property of linearity of the integral. Well, not linearity, but splitting up due to the limits of integration. Going on to the next slide, we're going to talk about the linearity property. So, going on. So what I said before was that we have linearity of the integral. Suppose that I give you the value of the integral of x squared from 0 to 1, which is 1/3. Then we are going to find the following integral. 3 plus 5x squared dx going from 0 to 1. Well, for this original integral, we can use the linearity property, which is that if I have the sum of two functions underneath the integral, then I can split it up as the sum of two integrals. Now for this first integral, the integral of a constant over an interval is the same thing as the constant times the length of the interval. I believe that this was the first property of integrals that we showcased. Now for the second one, I'm going to pull out the 5 because we know that we can pull out constants from an integral. And now we do a little bit of simplification. Well, this is just 1, so 3 times 1 is 3. Over here, I have 5 times this integral, but we're given the integral value. Then it's just simplification. So this would be 3 plus 5/3. If you wanted to get it all into one common denominator, then we'll just put this 3 over the 3. We'll get a 9 plus a 5 up top. And we have 14/3. So the properties that we used here are that if we have two Riemann integrable functions f and g on an interval a to b, then the integral of f plus g is the same thing as the integral of f plus the integral of g. Now that's not the only property I used. There's one more I'm going to put on the next slide. If I have the integral of a constant times a function, That's the same thing as factoring out the constant from the integral and multiplying it to the integral of the function. And lastly, if I have a constant c, which does not depend on x, then the integral of this c is just that c times the length of the interval. So essentially, just note that a lot of the properties of the integral we talked about can be used to quickly evaluate any integrals given to us, especially if we know some value related to the integral. Now, as far as our introductory properties, I think that this is going to be the last one I'll discuss. Suppose that we have the integral of x from 0 to 0, and we want to evaluate this. Well, this is actually a pretty simple answer. It's 0. And it's due to the following property. If I take a function and I take the integral from a to a, well, that's always equal to 0. Because if you try to get the lengths of this in your Riemann sum, sorry, not the lengths, but the widths of this, then the width of each rectangle is going to be automatically 0. And so if I add up a bunch of zeros, well, I'm still getting just 0. Now, these are just some of the introductory properties of the integral that I wanted to discuss. Now we talk about something that's a bit more thorough. So if f of x is greater than or equal to 0 on the integral a to b, sorry, not the integral, but the interval, then what do you think that implies about the integral itself? Well, then the integral of f over a to b has to be greater than or equal to 0 as well. And what that does is it gives us the following property. If I take f to be bigger than or equal to g on that same interval, then we have the integral of f on that interval is bigger than or equal to the integral of g on that interval. You always want to be careful and make sure you get your dx's down. You want to make sure that you never leave it ambiguous about what the integrating variable is. That's something that'll probably be a bit more important to us as we're doing the fundamental theorem of calculus section. But it is still something that you should be nitpicky with yourself about. You want to be clear what variable you're integrating to. Now, I said that you can show the second property 2 from the property 1. Well, let's show that. So we're going to show that 1 implies 2. And obviously this is about, integrable functions on this interval. So even though I didn't write the hypothesis, let f and b be integrable on a to b, essentially just any theorem or property I state here, take that as given. I'm not going to discuss functions which are not integrable. So for 2, let's suppose that we have f to be bigger than or equal to g. Then what does this mean about the difference? Well, essentially what I did was just subtract gx on both sides of this equation. So on the right side, we get that this is a positive function. Thus, 1 implies the integral from a to b of f minus g is greater than or equal to 0. But we have a property here that can help us. By linearity, so that means that if I take a integral of a sum, it's the same thing as the sum of the integrals. We have that the integral of f minus the integral of g is greater than or equal to 0. So just add that integral on the right to both sides. And what we have is that the integral of f is greater than or equal to the integral of g. And this is actually an analytic proof of the property. To be honest, you could take this a lot less rigorously. You can honestly just make a rough sketch, a good example. And I think that that's what I'm going to do for this next property. So going on to the next slide. If we have that f is between two numbers, little m and big M, on the interval a to b, then the integral from a to b of that same function f is going to be in between that big M times the length of the interval, and also greater than or equal to that little m times the length of the interval. Now what I'm going to do for this one is I'm just going to give a quick graphical justification. So this is not going to be an extensive proof, it's just sort of a rough general picture. And the reason why this isn't really a deductive proof is because I'm not going to consider, there we go. I'm not going to consider, all the cases, because we could have a countable amount of jump discontinuities and so on and so forth, but I wouldn't want to get bogged down in all that tedious notation. If I was doing an analytic proof for this, I'd probably say without loss of generality, consider continuous functions and the like, because we could break up regions and all that. But to keep it just a sort of simple picture, let's say that I have some function f, and it's continuous on this interval a to b. All right, we know it's integrable and everything. That's a theorem that I haven't stated here, but I did in class. And so I'm just going to reiterate it for those who are having a bit of trouble remembering this. If f is continuous, which I abbreviate as CTS, on the closed interval a to b, then f is what we call integrable. On a to b. I'll just make that e a little bit neater. And to be integrable just means that the integral exists as a limit for all partitions. Now, I think it's pretty clear that if I make this nice little red line, which I'll say call little m, that f is bigger than or equal to that little m on that interval, i.e. the curve of f lives above this flat line little m. Now let's suppose I take something a bit larger than the function, a nice flat line, capital M. Then I think it's pretty clear from everybody in this picture that the flat line M, capital M, is living above the curve of f between A and B. Now I'm going to take some areas here. So this area I'm shading in red, this is all the area underneath the little m. This blue is going to be all the area underneath f. And this green is going to be all the area under that big M. So the area underneath the little m, is that more area than the area underneath f? No, right? Well, the area underneath f is just the integral from a to b of f. But the area underneath m, you could think of it as the integral of little m on a to b, but you could also note that this is a rectangle with width b minus a and length little m. And a similar argument here shows that the blue area is less than the green area. And so I got this capital M times b minus a. So you now should be able to just give a general rough sketch of justifying why some of these boundedness things happen. Going on to the next slide. So we are going to bound the integral sine of x squared dx from 0 to, let's say, the square root of pi. Now, I just want to clarify here that this integral, it can't be found or evaluated using elementary integration techniques. Because even once we have the fundamental theorem of calculus, sine of x squared doesn't have an elementary antiderivative. So it's not just a simple functional evaluation. This integral is actually something that we call the Fresnel integral. It's just that the Fresnel integral is usually generalized for any upper limit of integration and treated as a function rather than just a definite value. Now, the general idea here is that we want to find a bound on our integrand sine of x squared. So the integrand sine of x squared needs to get bounded. And we know that this function is going to have bounds because we're working on a closed interval. So this is bounded on just 0 to the square root of pi. And we're continuous on that closed interval. And that's just from the composition of two continuous functions. So if I have a continuous function on a closed interval, then we know at the very minimum, we have extreme on there by the extreme value theorem. But what we can do explicitly to find those is the closed interval method. So using the closed interval method, I take the derivative. Now, if the derivative is sine of x squared, I have to apply the chain rule, and I'll take the derivative of the outer function, plug in the inner function, and then multiply by the derivative of the inner function, which is 2x. So this is just 2x cosine x squared. Now I'm going to make it clear now that this integral is never non-existent. I can plug in any x value into here, and I'll still have a number pop out. The derivative always exists. But that's not the only time we get critical numbers. We can also just check when the derivative is equal to 0. Well, I think it's pretty clear that the derivative is equal to 0 when x equals 0, but that's kind of irrelevant to us because 0 is one of the endpoints on our interval. So I was automatically going to check that value anyway. But it's also equal to 0 whenever cosine of x squared is equal to 0. And that happens whenever x squared is equal to, say, pi over 2, 3 pi over 2, so on and so forth, as well as, negative values. Or x is equal to the square root of pi over 2, the square root of 3 pi over 2, and so on. But what interval was I working over? I was working over 0 to the square root of pi. So I really only have to consider that value x at the square root of pi over 2, because it's in between 0 and the square root of pi. So now we have our critical numbers. What we do is we evaluate the function at our endpoints and at our critical values. So remember, we got to plug these things back into f, not f prime. Any critical values that I found, when I plug them into the derivative, I should get 0. And if I plug the endpoints into the derivative, I just don't really get much information other than I might be increasing or decreasing near that point. Now, f at 0 is sine 0 squared, but that's just sine at 0. We should know that that's just 0. If you don't believe me, plug it into your calculator. And just to let you know, please make sure that your calculator is in radians. For 0, it's not really going to cause you any issues. But for anything else I write down here, it's going to throw off your answers drastically if you're using radians rather than degrees. If you're using degrees rather than radians. Now, the only critical point I found on this region was the square root of pi over 2. Well, that's sine of the square root of pi over 2 squared. That's sine of pi over 2. For those of you who have been unfamiliar with your unit circle, sine of pi over 2 is 1. And now, last but not least, I plug in my other endpoint of the interval. So that's sine of the square root of pi squared. That's just sine at pi, which by our unit circle is 0. So f of x, which is sine of x squared, is in between 0 and 1 on the interval 0 to the square root of pi. So that means that the integral of sine of x squared is less than or equal to 1 times the length of this interval, but that's just the square root of pi, and I'm larger than or equal to 0 times the length of the interval, but that's just 0. And thus, we have ourselves a nice bound on this integral over that region. All right, great. So now we've talked about some basics here as far as properties, and we've talked about some, beefed up properties, comparison properties, bounding properties. Now let's talk about geometric interpretations. So we're going to evaluate from -1 to 2 x dx. Sorry, the integral of. Well, if we have the fundamental theorem of calculus, this is a very simple problem. But in this section, we're doing it in terms of areas. So what you do is you get yourself a handy graphing calculator and you graph the function. Now, you don't necessarily need to do this next step, but I do it because I think it makes it a bit more explicit. What you do is you graph the vertical lines that define your limits of integration. And what you're going to get are geometric figures. So basically what happens is that in this region that I'm circling my mouse in, this is a little bit of negative area that we get from our integral. And over here, this is some of the positive area that we get. And the thing is that we know some nice geometric formulas for these two figures. They're both triangles. So if I say call this triangle the positive area that I take on, and this one the negative area that I take on, then the integral of x dx is equal to the positive area minus our negative. Well, what is the positive area? Well, it's a triangle with a base of 2, a height of 2. So we get 1/2 the base times the height. Do a little simplification, that's just 2. All right. Now, if I take this and I just sort of think of this, well then, going to the left, I'm going a distance of 1 unit. Down here, another distance of 1 unit. So base and height are both 1. So this is like a 1/2. So the integral from -1 to 2 of x is going to be 2 minus 1/2. Well, that's just 3/2. And so we've evaluated a function's integral, but instead of using the fundamental theorem of calculus, we've interpreted it in terms of geometric areas. So if I just go back to the whiteboard, our argument there on that graph just says that this integral is equal to 3/2. Now, I'm going on to the last problem that I think I'm going to cover in this section. Now, if you understand everything up until this point, you can feel free to head out now, because this right here is just a fun little exercise that you can do if you know the property of linearity. Suppose that for each n, which is going to be 1, 2, 3, so on and so forth, basically let n be a positive integer, then we have the following. n minus 1 up till n of an integral f of x dx is equal to n. That is, the integral from 0 to 1 of f is 1. The integral from 1 to 2 of f is 2, and so on. So the integral from 2 to 3 would be 3, and we just continue that pattern. Then the integral from 0 to n is going to be the following. N times n plus 1 over 2. Now this uses a finite summation formula, but I think it's a fun little thing you can toy around with here. So the integral from 0 to n is like the integral from n minus 1 to n plus the integral from n minus 2 to n minus 1 all the way down to the first integral, 0 to 1. And the thing is that for all of these, we know their values. We know n plus n minus 1, dot, 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 until we get down to 1. But I mean, this is the same thing as just adding up all the positive integers from 1 to n. And using the finite sum formula that we know, this is exactly n times n plus 1 over 2. So just a fun little property you can deduce from linearity. In all honesty, I don't think that this would have something that shows up a lot in real life, but it's just something that you can sort of toy around with, have a little fun doing some abstract computation. Going on to the last slide here. What I'm going to leave you off with is just sort of a calculation that you can do using our boundedness theorem. And maybe you could, if you can't figure out the calculation itself, sort of think about what you would do to get there. So if f is integrable, on the closed interval, a to b, then the absolute value of the integral is less than or equal to the absolute value of f, and then taking the integral of it. This is definitely going to be something that uses your boundedness theorem, but just as a little hint, note that the function f itself is in between the negative absolute value of f and the positive absolute value of f on that closed interval. And this concludes the examples and sort of results that you can deduce from this section that I wanted to talk about in this video. Thank you for watching.